Hi class, back again with objective 2 and hopefully 3 on thinking. We'll see. Without further ado, here is my PowerPoint lecture and we're going to do it from current slide. Okay, so we're going to talk about the sleep stages, cycles of sleep, REM, and dreaming. So the EEG stands for electroencephalogram, and that's how we record brain activity during sleep, one of the ways in which we do it. And it is electrical activity that's recorded through the scalp. So just like on the picture, you put all these electrodes on the scalp. And because neurons are sending off electricity, we can detect some of that. It kind of helps us to record synchrony of neurons. So if they're all firing in the same way, then we call it synchronous. And it helps us to define the different stages of sleep. So let's look at those. If you're awake, the brain waves seem to be real choppy and short. And then as you start to go to sleep, stage 1 is your first stage of sleep, 2, 3, 4, and you can see they change a lot and the waves get further apart and they also get larger in amplitude. But then look at REM sleep at the bottom there, and you can see it looks a lot more like when we're awake or stage 1 sleep. So it's a much lighter stage of sleep. So we'll talk about that in a little bit. So when we're awake and relaxed, we've got what are called alpha waves. And those are those really choppy little waves, right? So even though we're pretty relaxed, our waves are just, our brain's pretty busy. In stages 1 and 2, we start to see, again, a high amplitude relative to other stages and low frequency waves. So sleep spindles happen back in stages 1 and 2. And a sleep spindle is this little area of activity, little bursts of activity that happen in stage 2. And we're going to see later on that those are associated with learning. Stages 3 and 4 are involved in slow wave sleep. And during that time when those waves get really big down here in stages 3 and 4, we start to see that our heart rate slows down, our breathing slows down, and the brain waves become very synchronized. In stage 4, the thalamus stops sending sensation to the cortex. So it's really hard to wake somebody up during that time. So even if there's noise in the room or whatever, the thalamus kind of stops it before it goes to the cortex. Now, if you're very prepared for a particular noise, for example, you got to wake up and go to the airport or something and you're waiting for that alarm clock, then it'll send that through. Your thalamus has a way of knowing when it's very important. If you have a baby, for example, the baby cries, even if you're in stage 4 sleep, you'll hear that. But in stage 4 sleep, we don't hear too much, usually, if it's unimportant. So age-related changes having to do with sleep. Here you see the newborn infant is sleeping every couple of hours and just all day long. By the time they're 1 year old, you get a couple of naps, but the sleep is quite concentrated already. 4 years old now, you don't have, you just have 1 nap. Then 10 years old, no naps at all. And adult, you can see from the 10-year-old to the adult sleeps quite a bit less, and you might find that you sleep less as time goes on. I know I don't sleep really ever 8 hours a night, but I used to sleep 8 or 10 hours a night. Okay, well, paradoxical or REM sleep is that stage where, again, it gets real choppy again, almost as if you're awake, but you're not, and your brain is active, but your body is not. So a lot of times we call this paradoxical. A paradox means a riddle, because your body seems really paralyzed during this time. Your eyes are moving, your heart rate and your breathing is up, so you seem a little bit more kind of on the awake spectrum. But then there's some weird things. Your body doesn't move. You get these sexual responses. So men will get an erection during this time. Women will tend to get vaginal lubrication during this time. Twitches are common, but again, no real movement. You don't tend to turn over and stuff like that. It is associated with dreaming, and we think one of the reasons why we don't move is so that we don't act out our dreams. Okay, so how do the cycles of sleep go? When you fall asleep, as long as you stay asleep, it'll go stage 1, stage 2, stage 3, stage 4, and then 3, and then 2, so you're kind of coming out of sleep in some sense. But then rather than go back to stage 1, you'll hit REM sleep. And after REM, you'll go to 2, 3, 4, 3, 2, REM, 2, 3, 4, 3, 2 REM. So we go kind of up and down in these sleep stages all night. And the only time we go to stage 1 is when we're falling asleep from wakefulness. The entire cycle will take about 90 minutes. And as the deeper sleep occurs earlier in the night, the REM sleep tends to get longer later in the night and in the morning hours. So you can see that here, REM sleep, you can see these bars of red REM sleep. The longer you sleep, the longer your dreams will get. They tend to be really brief earlier in the night, but just before you wake up, you usually have longer dreams. Okay, I want to talk a little bit about the brain mechanisms of sleep and arousal. One of the things we saw early on in sleep is that if you cut the reticular formation, which is a band of fibers in the midbrain area, you cut this pontomesencephalon, and that's part of this reticular formation in the midbrain. What happens is it's going to be sensory afferents bringing up sensory information, and once you cut that, the animal goes to sleep. So what happens is that these wake-up signals are not coming to the basal forebrain. The basal forebrain, the bottom of the forebrain, is what's really going to wake up the rest of the brain. And it's going to do that using acetylcholine. We'll see that a little bit later. Stimulation of the pontomesencephalon will also stimulate the cortex through the basal forebrain. Okay, a few other areas. Well, we talked about the basal forebrain. That's going to project to the cortex using acetylcholine for excitation. The damage to that area causes low arousal and pretty poor learning just because you just don't have the arousal enough to learn. You know, when you're very tired, it's hard to learn things. So that happens in Alzheimer's disease. We do see that. So the basal forebrain is really, really important. We've got a couple of other areas that are important. The locus coeruleus is in the pons, and when it's active, we learn and remember better. And so it's not really waking up, but it's more like becoming alert when something is important, you know. So it uses norepinephrine, and it kind of wakes up the brain when you hear something important. You go, oh, okay, this is on the test. Oh, okay. You know, you kind of alert yourself, and that's your locus coeruleus doing that. The hypothalamus is also involved in alerting us by releasing a neurotransmitters called histamines, and also orexin. And the histamines, if you've ever taken antihistamines, you know you get drowsy, and that's because it's blocking those histamines in the hypothalamus. So the histamines do wake us up if we are asleep. Also, orexin is involved in staying awake during the day. And so what we're going to see is people with narcolepsy tend to lack that orexin. There's some of the cells that use orexin start to die in the hypothalamus. So in order to go to sleep, the cells in the basal forebrain are going to release GABA, and that is an inhibitory neurotransmitter, and so that's going to kind of put the rest of the cortex to sleep. And then they also put out a neurotransmitter called adenosine. And adenosine is also an inhibitory neurotransmitter, and it tends to build up as the day goes on. And at very high levels of adenosine, we start to get sleepy. So at the end of the day, we got enough adenosine and we start to get sleepy. Well, interestingly enough, and I think what's interesting about adenosine is that caffeine tends to inhibit it. So if you take caffeine in the morning or afternoon or evening anytime, it will end you with less adenosine at the end of the day, and then you get less sleepy at the end of the day. So if you're having trouble sleeping, always a good idea to get yourself off of caffeine. Okay, well, let's take a look at some of those pathways there. We see from the pontomesencephalon, which we started to talk about, going up, we get acetylcholine release to the basal forebrain here. The basal forebrain is then going to do acetylcholine to the rest of the brain. That wakes us up. The locus coeruleus here in this purple line does also use the norepinephrine to wake up the basal forebrain to, again, wake us up. And then we've got the hypothalamus there that's going to be using serotonin again to wake us up. So we'll talk about, we'll review some of these in the next slide here. So in order to wake up, we're going to be using the reticular formation. It's going to be using ACH to the basal forebrain, and then to the basal forebrain will wake up the cortex. The locus coeruleus also, uses norepinephrine to wake us up. The hypothalamus is going to use histamine. Both of those feed into that basal forebrain, which wakes us up. When we're going to sleep, we have low sensory information coming in, so not so much noise, not so much light. The reticular formation is relatively quiet. The basal forebrain then gets relatively quiet. And then we start to see the action of GABA and adenosine on the cortex coming from the basal forebrain there. So that's just a review of those areas, the top part being waking up and the bottom part being going to sleep. Okay, so what happens with REM? REM, the brain activity that we see during REM is the pons and the limbic system, the parietal and temporal cortex become very active. But there's less activity in V1, which is the occipital cortex, primary visual area, and prefrontal cortex and motor cortex. So you can imagine what that looks like, right? We start, the activity increasing in the pons is going to lead to a kind of paralysis of the body, and then that's going to prevent us from acting out our dreams. And then with the limbic system, you can imagine that dreams are very emotional, so that area is improved. The parietal and temporal cortex are involved in visual information. So dreams are also very visual, but there's less activity in the primary visual cortex, which is in the occipital lobe. So it's not actual vision, and because we're not getting input from the eyes. Prefrontal cortex are involved in reasoning. We're not getting that clearly in dreams because that's why they don't make much sense. And then the motor cortex, because again, we're not ordering any movements at that time. So we get these things called PGO waves, which is pons geniculate occipital. And I'm going to show you that in a minute. Recognize that increasing acetylcholine will tend to increase REM. Now we see that acetylcholine kind of wakes us up. So that makes some sense because if you increase acetylcholine, you get to lighter stages of sleep and eventually to wakefulness. And REM is a light stage of sleep. Increasing serotonin will tend to inhibit REM. And there we have some of the serotonin agonist drugs like, for example, the SSRIs used for depression that will tend to actually even knock out REM and knock out dreaming if you take those drugs. Okay, well, here's your PGO wave. This is what's happening when you're dreaming. Now, normally, you would think that information from the eyes would be coming to the lateral geniculate, would be going to the occipital lobe. You learned that in the vision chapter. But now we're talking about information coming in from the pons. So information coming from the pons is going to go to the lateral geniculate, which is normally about vision, and then to the occipital cortex. And we do get that again during dreaming, during REM sleep. Now, remember, it's not V1 back here. It's some of the other areas of the occipital cortex that are active. And we certainly get activity in the parietal and temporal lobes as well, which leads to some of the visual sensations in dreams. Okay, we'll hit chapter 4, or objective 4 next time. Sorry for the long video.